quotient property for square roots. So for positive values of a and b and non-zero b, the square root of a quotient is the quotient of the square root. Well, all that means is that we can split up square roots into individual radicands as long as there's pure multiplication or division. In this case, division, right? Hence the reason it's called a quotient. So our example states that square root of a over the b is equivalent to saying the square root of a divided by the square root of b. And hence our example, square root of 25 over 36. But before we go into that example, let's go through a more complex example, and then I'll come back to this one that's a little more basic. That way it's easier to visualize. So let's say, for example, I give you square root of 35 over 48. Okay, so according to our quotient property, we should be able to split those up. So splitting them up into radicand on the bottom and radicand on the top, square root of 35 over square root of 48. And now, let's try to simplify this. Let's do this through prime factorization. Probably makes it easier. Prime factor 3, in other words. Let's see, 35. What two multiples give us 35? That would be 5 times 7, right? 5 times 7 is 35. Hey, look at that. Both numbers are prime numbers. So technically, I can't take the square root of 35 unless I want to get a decimal value. For this case, let's leave it with an exact value for now. So let's assume we want an exact value. We can get a decimal approximation towards the end if needed. So that means we're gonna go to the 48. 48, prime factorization of 48. We can go the lengthy technique or we can practice our multiplications. Highly recommend you practice your multiplications, agreed? But let's make it the easy way, lengthy way. It's not too bad though. In other words, half. Half of 48 is 24, meaning it's a multiple of 2. In other words, 2 times 24. And it looks like 24 is not a prime number, so therefore we can go half. Half of 24 is 12. So in other words, 2 times 12, agreed? Keep in mind, half means a multiple of 2. All right, so let's go ahead and go one more step because 12 is not a prime number, so half of 12 or 2 times 6 will give us 12. And then 6 is still an even number, so 2 times 3 will give us 6, or half of 6 is 3. There we go, we got the full prime factorization tree for 48. So in other words, what we want to do now is circle pairs of numbers. There's a pair of 2's, and there's another pair of 2's, which I've highlighted there for you, or circled, sort of encircled, I should say. And the 3 has no pair, so in other words, it's by itself. But I'll just restate it down below as 2 squared times 2 squared times 3 to make your life a little bit easier to visualize. Notice that that square is coming from the fact that I have 2 of them on there, and the other square is the fact that I have another pair of 2's. But if I multiply 2 squared times 2 squared times 3, my answer should be 48 again. Agreed? Double check with your calculator, just in case I missed it. So now that I have my prime factorization, I can go ahead and go back through and plug it into my formula up above. So 35, unfortunately, I can't go past 5 times 7, agreed? And those are both prime numbers, so I can't simplify that any further. So square root of 5 times 7, I'm going to have to leave it as square root of 35 at the end. But on the bottom, square root of 48, I can convert it to 2 squared times 2 squared times 3, but let's remember the radicand, square root of all that, right? Square root of 2 squared times 2 squared times 3. And I can also simplify by making it into individual radicands, product property for square root, right? That's our next step. Square root of 5 times 7, well, 5 times 7, I can't simplify any further, so 35. So in that case, individual radicands, square root of 2 squared, square root of 2 squared, and square root of 3 on the bottom. Notice that my squares and square roots cancel each other out, right? So that way I'm left with just the 2's on there. Okay, I'm going to go to the bottom for my next step as in the eventually because I'm going to run out of space, right? So there we go. 2 times 2 times the square root of 3. Notice the 3 I couldn't cancel out the radicand because it does not have another pair or another multiple of it. Agreed? So in other words, 2 times 2 gives me 4. And I have the square root of 3 still underneath. We tend to not enjoy having a radicand in the denominator. In other words, the square root. We do not want to have a square root in the denominator. So in the event, we will have to rationalize the denominator, meaning get rid of the square root from the denominator. What that implies is we still have the same expression, square root of 35, divided by 4 times the square root of 3, but the only difference is we're going to multiply by the same number as what we have in the bottom, the square root of 3, in order to make it a square and be able to get rid of the radicand, or the square root. So there we go, square root of 3. on top times the square root of 3 on the bottom. And just for reference, square root of 3, well, 3 times 35 will give us 105. Combine it into one single radican again. But on the other hand, on the bottom, let me put a note on the bottom. So reference note for you, that way it makes it easier to visualize. What happens? So square root of 3 times the square root of 3. This is just looking at the bottom portion, okay? The top is 35 times 3 gives you 105, and it goes into one radican. But the bottom, square root of 3 times the square root of 3 portion, well, there's two square roots, right? That means that we have 3 square and then square rooting it, or vice versa. That means the square root and the square will cancel each other out, leaving us with just that 3. So overall, on the bottom, it becomes 4 times 3. 4 times 3 would be 12. There it is. There is technically our final answer. Pretty close, other than me missing a plus or minus there, right? I'll write it in a few minutes. But otherwise, let me go back to real quick. Alternate way of getting a prime factorization tree for that 48. We could have chosen 48, but also chosen 8 times 6, and we would eventually get down to a prime factorization of 2 squared times 2 squared times 3. Do be aware about that, okay? So that is an alternate way of doing this as well. This should work technically. And of course, now let me backtrack a little and enlarge this. That way I can have a plus or minus sign on there. There we go. My answer needs a plus or minus since it is the square root. So plus or minus the square root of 5 over 12 is technically my final exact value answer. And if I wanted to get an approximate answer, I could probably put that on my calculator. Probably want to try on my calculator, clear anything I might have. And then, well, if I can have my calculator in there, we second. And then my button would be the square root. Notice I have a square there. That produces the square root. And then I can put 105, close my parentheses, hit the division sign, and then put 12 and hit enter. Then I get my decimal approximation of plus or minus 0.8539 roughly. Okay, I'll leave that one up to you if you want to approximate or not. But going back to our original expression, square root of 25 over 35, that's another example, right? So another example, let me get rid of this here. Square root of 25 over 36, keep in mind, just to recap, we can split up into individual radicands, square root of 25 or square root of 36. Hey, what is the square root of 25? Did you say 5 by any chance? And what is the square root of 36? Did you say 6 by any chance? Well, sometimes you don't have to rationalize the denominator. Be aware of that. Sometimes you get an exact fraction or exact decimal, like in this case. Do be aware though, the only thing I'm missing on there is a plus or minus depending on what my question is talking about. So plus or minus 5, 6.